Welcome to today's session where we'll meet Brian Huff, Vice President of Technology at Sandvik-owned Artisan vehicles. We will discuss how far the technology has come and how Sandvik has addressed safety and productivity in battery electric vehicles, BEVs. Welcome to today's session, Brian.
Hi, thanks. Thanks for having me.
Thank you. And thank you for joining us online too. Post your questions in the comment field and we'll try to address them as we go. And just for your knowledge, Brian has agreed to do a Q&A session if we don't have time to get through the questions. So just keep them coming. Right, Brian?
Yeah, absolutely.
Good. So, Brian, you have really dedicated your career to BEVs. I know that you spent no less than 9 years at University of California at Davis, and I looked it up online, and it said that the alumni are go-getters, change makers, and problem solvers. What about that?
I can't disagree. I guess that's that's kind of been the plan from the outset: find a challenge and look for a solution, right? Yeah, it's been a long time. 9 years makes it seem like I should have ended up with a PhD, but I ended up with a master's degree. I spent a lot of time doing research and working on projects. So it was it was a really good time.
And then, can you elaborate a little bit about your background?
Yeah, so I started working on hybrid electric vehicles actually in 1994. So it's been 26 years of working on electric drive and hybrid vehicles. At the time, it was back when we were in that transition between nickel cadmium batteries and nickel metal hydride batteries. So I've really kind of seen the full evolution of the battery technology for vehicle use. And it's been quite an evolution for sure. In the 90s, it was really hybrids were the only solution that was really viable. You couldn't get enough batteries in the vehicle to get more than 120 miles of range or so. And then at that, the batteries were quite large and heavy, so it was challenging to say the least to build a vehicle around them. I worked at the university doing work for the Department of Energy and some defense projects, a lot of automotive projects for testing out hybrid vehicle designs, powertrains, and battery systems. And then I started at California Motors in 2003. And there we started with a hybrid electric supercar, which was our original plan. And through the years, we did a lot of military work, a lot of concept vehicles for other startup OEMs, some work with Volvo and with BMW and Porsche, Roof Porsche in Germany. We did an electric 911 for them. So we had quite a few automotive projects. And then 10 years ago, we got into mining. And that really kind of changed our whole focus and changed my whole focus, and kind of been in my career since then focused entirely on mining equipment and solving the problems there.
Thank you, Brian. And there has been a few questions already, and there have been a couple questions about the battery composition in the comments and the safety of it. Can you let us know what the battery composition of Artisan battery is and the safety of that composition before we dive on further?
Sure. Yeah. So we use lithium iron phosphate cells. They're a lithium ion battery, but they have a lot safer chemistry. And this is a common question. Everyone is asking about safety. Especially with the Samsung phone issues a few years back, the Dreamliner battery incidents, those silly balancing scooter things that were catching on fire. There's a lot of history of personal electronic devices and lithium ion batteries that have been catching on fire. And so the concern is 100% justified, but there is really a key difference in what we're doing. These cells use a totally different material. Those cells in personal electronic devices are cobalt oxide, and the oxide part of that cathode material really kind of oxygenates the reaction. And when you get a fire, it's a lot more aggressive. And lithium iron phosphate burns much more slowly. It's still flammable, but it's flammable in the way that more mundane materials like firewood would burn. And so it makes it a lot more containable, and allows us to build a system that can keep incidents like that from propagating, getting out of the battery pack. You still, of course, if you burn it, it will burn, but it's a lot safer and a lot less aggressive. And that really makes a critical difference, especially for the mining application.
Thank you, Brian. And to get going here, I know that there are 3 different generations of mining BEVs. And I think to start up, can you explain those to us?
Yeah, and this is something that we've kind of been involved with, for the last 10 years. The generation 1 implementation, the first one that we did, was the simplest that it's probably the way you would imagine doing it if you came across this project to begin with. You just take the engine out, put an electric motor in, and try and leave as much of the machine the same as possible. So that keeps the torque converter, keeps a multi-gear transmission, uses the power takeoff from the transmission to drive a hydraulic pump, all the conventional hydraulic systems, standard valving. So it's really the same machine, just take the engine out, put an electric motor in. That was kind of the generation 1. And you definitely get, zero emission. It's running on battery now, less heat is generated. But there's still a lot more you can do to improve the efficiency. And one of so that takes you to the generation 2 design. And that's where you take the next step, which is to take out the torque converter. And then in order to drive the hydraulics, you need to add an extra electric motor to drive a pump. And that allows the traction motor, we call it, to not rotate when you're idling. And you can decouple the power draw and have the hydraulic system driven independently of what's driving the wheels. And that really improves the efficiency a lot. Getting rid of that torque converter makes a monumental improvement. And you get better regenerative braking efficiency. So overall, a lot better performance. But still, with the generation 2 approach, you're still using a machine that was designed around a diesel engine. And if you're familiar with the requirements for ventilation in mining, most jurisdictions require a certain amount of ventilation based on the installed horsepower. And so when you're designing a vehicle like that, you're going to try and put the smallest engine you can into the machine to get the job done. And then in order to optimize the use of that limited amount of horsepower on the machine, you have to make the machine as light as possible. You design the drive line around that smaller engine. You drive the drive shafts, the axles. Everything is really kind of built around that smaller engine. With battery electric, we no longer have that restriction. But in order to use that higher power capability, you really have to build the machine around it. And that's where a generation 3 approach comes in. We scrap the entire machine, start from scratch, and select the driveline components, axles, and everything, frame design, everything is kind of built around this higher power capability. And we can also build in really critical features like battery swappability and self-swapping. In our machines, you actually drop a portion of the frame on the ground in order to swap batteries. That's not really possible in a machine where the frame has really been designed as a single unified structure. So this new start from scratch approach, this generation 3 approach, has really allowed us to rethink the vehicle as a whole and build it around what's capable, what the capabilities are of battery and electric drive.
So rethinking design, could you just quickly sum up why rethinking the design and discard as much as you can about conventional diesel engineering is so important when, designing a battery electric loader or haul truck?
Well, as I said, it's really about starting from scratch and getting the most benefit you can from your electric drive, getting more power into a smaller machine. And that allows us to do much more in a smaller package, which for mining, of course, the smaller the machine, the less waste development you have in order to get the valuable materials out. And then this, I can't stress enough also that this ability to swap batteries quickly and efficiently is a real enabler, and that's really only viable with a ground up approach. The ability to do that swapping without a crane and without a significant infrastructure in the mine to do it.
Okay, and for you who just joined, we're here with Brian Huff, Vice President of Technology at Sandvik-owned Artisan Vehicles. We're talking about BEVs and how they are coming into our industry. So, Brian, when it comes to productivity, Artisan Sandvik BEVs are known for outperforming their weight class. How is that possible?
Yeah, it's really about there's a couple kind of key enablers. For our loaders, the fact that we don't have transmission gives us a lot more flexibility, right? So for those machines, we're able to put large wheels in the front that are designed to carry, and large tires that are designed to carry the payload of the machine. But then in the rear, where there isn't an increased load while you're operating, we can put smaller tires. That gives us a much better visibility out the rear of the machine and allows us to fit more into that smaller package. And then we also have redesigned the boom structures to move the pivot location down. And it's just a kind of a new approach to that geometry, and allows us to keep that visibility while still maintaining the lift height of the larger size class machine. So we've done that with our 10-ton loader, the A10, where it's essentially the same size as a 7 or 8-ton machine, but has the same lift capacity in both tonnage and height as a 10-ton machine. And again, because we're designing from scratch, we're able to put more power into the machine. So we get tractive effort that's higher than even the most competitive 10-ton machines, but still in a smaller package.
Okay. And could you give an overview of the Artisan Sandvik family of trucks and loaders and how the matched models in different classes help optimize the load haul cycle?
So right now we have a 4-ton machine, which is really intended for like narrow vein type applications. And then we have a 10-ton loader and a 50-ton truck. Is our current product offering, and then there'll be a new machine launching next Tuesday, and I'll leave that one for the announcement on Tuesday. But it's going to be another machine to help fill out our weight class here. We've got a few more in the pipeline in order to really get the full product range, but those will be coming in coming years.
We actually got a question about that right now that I want to read to you. Is that all right?
I'm not sure how much I can say, but I'll
but
try.
It's just a simple question. It's actually from Daniel Gleason. He's a mining journalist. When will you be able to deliver a machine with more than 50-ton payload? You don't have to answer, silent period coming up and everything, but of course.
Yeah. I can't give a date right now. The product roadmap, though, we have talked about it a bit, and there will be a larger class machine, haul truck, intended largely for the Australian market. And we get a lot of questions from down under about higher capacity machines.
So to answer his question, eventually there will be.
Eventually, yes.
That's vague enough. Good. Thanks. And we already talked about the battery composition, but for those who just joined, could we kind of recap about the use of lithium phosphate battery technology and some of the safety benefits of this battery chemistry? Just the safety benefits now.
Sure. Again, there's quite a difference, and I'll go a little bit in more detail since we've already kind of touched on it. The cathode material in the cell is really the differentiator between most different types of lithium-ion batteries. And what we're looking at in selecting a safe chemistry is the rate of combustion. So essentially how hot it burns, how aggressively it burns when a thermal runaway condition occurs. And our cells burn at 1/100th, 1% of the rate that even the next level up, nickel, the blended cathode NCM burns. So that's a dramatic change, which again minimizes, it keeps a failure from propagating through the battery pack, and it keeps a fire in the battery pack from leaving the battery pack. And that's really a critical difference in the chemistry and the choices that we've made. Beyond that, of course, there's kind of two approaches for battery protection, right? You try to make it more intrinsically safe and less volatile, and then the other half of battery safety is prevention. And you can go really, really in depth with prevention, and of course that is a primary focus. Battery monitoring systems, management systems, cooling systems, all of that is about prevention, but nothing is 100%. There's always failures, either from external forces, external fires, other considerations that are unpredictable and unpreventable. And so for those is why we've selected a chemistry that has a less volatility.
Yeah, thank you. And what about the power needs to keep a fleet of battery charged loaders and trucks running?
That's one of the benefits of swapping is really kind of around that. We see that more and more, as the discussions about battery electric vehicles have gone on. Initially it was about, should we do this? And now it was a, can we do this? And then now it's getting to the point, how do we do this, right? And now everyone is looking at their mind and thinking, what does it take to implement these machines? We've proven that they work. We've proven that they're productive. We've proven that they're valuable. Now everyone's looking at the details of what is the impact to my specific operation. And one of those that people start to realize is that if I'm powering all of this, my entire fleet of trucks or loaders from electricity, I need to supply that electricity. And that's enabled in large part by this. Our swapping technology allows us to charge the batteries at the same rate that the machines are consuming them, which really is the minimum power draw you can achieve, right? You can't ever, if you want to maintain operation, you have to have supply power at the same rate you're using power. But if you don't swap batteries, you have to put all that energy back in a short period of time while the machine is plugged in. With a swapping strategy, you can charge the battery while the machine is running, and it's kind of like your cordless drill. You swap batteries periodically, and you can maintain continuous operation. And at that same time, the charge rate is as low as it can possibly be to minimize that impact.
I know that there is a video prepared that's showing a battery swap. Could you then tell us about the battery swapping and also about charging it while we watch it together?
Sure.
Okay, let's watch it. So
I won't see it, right?
No, you won't see it. You just have to. It's the 50 seconds version.
I've seen it before. So, but yeah, the first operation, we pull into the charge bay, the charge location or swap area, and you have to get out of the cab. Right now, you have to get out of the cab and unplug the main battery packs, and then you get back in the cab, and there's a second battery located in the rear of the machine that powers it while you're doing the swap. And so then there's hydraulic work arms that lower the battery to the ground, and then you're able to back up and realign with the charged battery, pick it up, and then it locks into the machine to tie its frame structure into the rest of the frame of the machine. And then you get out and plug in the charger to the battery you just dropped off, plug in the battery that you just loaded, and then get back in the cab and drive away. And all in, that process takes about 6 minutes. And that's me doing the swap there, and I think that was my second try. So it's not terribly difficult. I'm familiar with it, but it is something we've seen our operators at the mines where our machines are deployed, and they almost they see it's a point of pride that they can do the swap in less than 6 minutes. So it's the longer they do it, the more effective and efficient they get it.
Thank you. That was very well explained. It was very well tuned to what was going on.
Yes, I've seen that video too many times.
Yeah. And also, there are some misconceptions among mines that haven't evolved to battery-powered equipment yet. And what are those, or some of those?
I think a lot of our potential customers think that they have to kind of think the entire mine in order to implement these technologies. And it's really not as hard as people think. And I think that's been a message of ours for a while. And it's largely, I think, enabled by the self-swapping capability. You don't have to have a big build out with a high back height and a big crane installed in order to swap batteries. We've deployed machines at mines in a matter of days, using existing jumbo plugs to run the chargers and a passing bay on the ramp in order to swap batteries. Using existing spaces and existing infrastructure, we can deploy quickly and easily. And so that kind of shift in the perception, I think, is important. This is attainable and it's doable now. Another thing is people think that there's going to be this big limitation in what you can do. And I think people probably felt the same way about electric drills, cordless battery operated drills, hand operated drills, what was it, maybe 20 years ago when they started to hit the market. And then quickly realized that they actually get more performance and just as productive operation out of those new cordless drills as they did out of their corded ones, and they're a lot easier to deal with. I think the same thing is happening with battery electric mining equipment. You use them the same way. There's also this perception that our trucks are going to have a limited range on ramps. And to kind of overcome that, we put together an animation of a 13 kilometer haul on a 1 in 7 ramp, or 14.5% ramp.
Yeah, we can actually, we can watch it now, because then you can talk about it, because it's basically how you then will set up the charging stations, etc. So let's see it, and you can talk about it. It's running.
So the idea, the only difference with this long haul application is that we add another charging station and one more battery. So this truck on this cycle is using 3 batteries instead of 2, and it runs 3 kilometers from the bottom when it picks up a load, and then swaps to a fresh battery. And the battery that it dropped off could be around 23% or so. Then it drives 5 kilometers up to the next swapping station, swaps batteries there, continues to the top another 5 kilometers, making a total of 13 to the top. And then at the top, it dumps its load and descends, and the descent charges the battery back up, the one that was still in it, and just charged back up to 66% to start the cycle over. So that recaptured potential energy of the empty truck is enough to take the battery from 23% back up to 66, which gets it back up to the first swapping station again. So it's quite a simple process to do. There's still margin in this. We could even go a little bit longer, but I wanted to put this together with room left. So you're not taking it down to no energy in the battery pack, to kind of demonstrate that this is feasible. And I think 13 kilometers is quite a long ramp, even for the Australians who do a lot of portal access, really deep haulage ramps. But we can basically tackle any operation. And along with that, the fact that the machine travels faster and doesn't have a diesel refueling time delay, which usually takes 30 minutes and happens maybe once a day, once every other day, we actually have better productivity than a conventional diesel-powered 51-ton truck. So it's really a no-compromise solution.
And then there's another question regarding this, that we're talking about multiple battery swaps. We don't know if new people have come on board, but how demanding are the infrastructure requirements for operating an Artisan Sandvik BEV?
Well, as I was talking about in terms of power draw from your grid, having a swapping architecture really minimizes that as best as possible. You adjust your charge rate to match your rate of consumption so that your battery is charged right when you need it, and that really minimizes the impact on the grid. And one other thing I didn't mention before is, we're talking about the underground power consumption. But if you're able to decrease your ventilation or decrease your cooling costs, then you may end up, not just cost, your ventilation power and cooling power, you may end up with a total power draw for your operation that's lower when you convert to battery equipment. even though you're powering your trucks and loaders, that the offset in fan power and cooling power can be quite substantial. We have seen that in some cases that especially when in a cold weather operation where you're doing electric heating, the power savings can be dramatic. And we've even seen case studies where like diesel generator powered mining operations can see a real benefit in their total diesel consumption because they're able to turn their fans down, and that more than offsets the power draw from the added equipment.
So it's complex to look at it.
It's complex.
Yeah. Thank you, Brian. I would like us to answer some questions from the audience.
Sure.
We have one from John Almond. He's the Director of Operations at Golden Star Resources. And he wants to know, how many times per shift do you need to change the battery in a 50-ton truck?
Well, the common answer is that it depends. And it depends largely on how efficient your operation is from a logistics standpoint. We've seen if you have everything dialed so that the truck is never waiting to get loaded or loading from an ore pass or chute and dumping into an ore pass where there's no backup or traffic, then you would need to swap batteries roughly every 2 hours. And again, the swap is only 6 minutes. And so we've still seen, even if you're swapping every 2 hours and you have an 8-hour shift, you could imagine 3 swaps or so in a shift. But even with that, you spend 18 minutes swapping, and our overall productivity would still be improved over diesel machines because we operate about 10% faster on the ramp. But what we've seen typically is that there's traffic. You're waiting for loading. You're waiting for your chance to dump, and a lot of those things really impact the overall battery runtime. And on average, for our deployed fleets, our battery run times are 3 to 4 hours typically. Thank you.
We have a few more questions from even before we started this session. There is one from Vladimir Milisaljevic. He's an associate professor at Belgrade University, Faculty of Mining and Geology. He wants to know information on energy density achieved and details about fire protection measures for battery electric vehicles. Maybe you already replied to that to some extent.
Yeah, I don't have the energy density numbers off the top of my head, but it's interesting because the mining application is quite different. That so much so that energy density really is not as important for us. We have more room. I mean, I would say energy density is more important than specific energy because we care even less about weight overall. This is, again, it's all in percentages of a 50-ton truck carrying 50 tons. But we actually the cells themselves are quite good. We put them in a really kind of around safety. Our enclosure and our system design has lots of safety protections. We've designed our battery to be serviced underground. The one thing that people may not realize is that these batteries really are a consumable, and they are more akin to diesel fuel or oil for your machine than anything else. It's not a piece of that's going to stay with the machine its entire life. The batteries will need to be replaced at some point. And so we've designed our system to allow that to happen underground in less than a shift. And that allows a battery refresh to happen safely and simply. But along with that comes a little bit more structure, a lot more packaging. And again, a lot of that's about containment of any kind of incident, thermal runaway that would occur in the battery pack. We also have fire suppression systems in the battery pack that are designed to put out the other materials in the pack. And so there's a lot there. Then they do kind of, unfortunately, work against each other, right? higher density is more volatile and more dangerous. Putting more space, more containment increases our safety, but it is at the detriment of energy density.
Okay, thank you. And the next question for you, Brian, is Is BEV technology more beneficial for greenfield or brownfield operations?
That's a good question. You probably could get more benefit from a greenfield operation. I think one of the more significant ones that maybe is not totally obvious is if you can build a mine that doesn't have any diesel at all, you can save all of that diesel fuel delivery and storage infrastructure, and it's relatively costly. You can also optimize the size of your headings for our smaller equipment. And smaller headings, this gets into a little complication for ventilation design, but ventilation isn't always just about clearing diesel particulates. It's also about dust clearing and blast gas clearing. And for dust clearing in particular, there's a minimum velocity that you need to achieve. So if you're doing a mine from the ground up, designed around a lower ventilation flow, you can optimize the heading sizes in order to achieve dust clearances that you need without having to have really high flow rates. So there's an advantage there. There's another possible advantage in operating with a downhill haulage scenario. And that's a really, really intriguing concept because essentially you're utilizing the potential energy of the mass of your ore to fuel your trucking fleet. And you can essentially get to the point where you almost never need to charge, which is really hard to imagine, but you could charge once every other day in some scenarios. And that has a distinct advantage. The challenge is, of course, then you have to run your shaft all the way to the bottom of the ore body and then mine upward, which increases the initial cost of the shaft, but you can end up with a pretty significant benefit in the end.
Potentially, could you end up with more energy than you can consume and then use that energy?
The only way that happens, and it can, is if the ore weighs more than the machine, right? If the mass of your ore, and it has to weigh more than your machine by enough to overcome all the losses, right? This isn't perpetual motion, but yeah, if you're carrying more than your truck weighs, then there's an opportunity there to end up with a slight surplus of energy. The point though about greenfield versus brownfield, I think I wanted to add though that even though there may be some new benefits from a greenfield operation, by no means does that mean that brownfields shouldn't consider it. I think we've really built our technology around enabling brownfield operations to take advantage of the technology and minimizing that infrastructure, minimizing the amount of investment they need to put up front in order to start deploying these machines. You don't have to convert the entire fleet. You don't have to put in millions of dollars of infrastructure. It's really something that can be done easily, and the machines operate exactly the same way your current machines do. You don't have to change the way you mine. You don't have to change much at all.
Okay, thank you. So just for a recap, we are here with Brian Huff, Vice President of Technology at Sandvik-owned Artisan Vehicles. We're talking about BEVs in the mining industry. And we have another question for you from Andrew Boyd, innovator of mining autonomy. Wouldn't shift or daily service still be required for checking hydraulics, greasing, or general checks?
Absolutely. And I wish more people did that. But yeah, greasing and oil checks are pretty similar. Of course, we have auto greasers and the machine kind of inherently has a lot more sensors. So most of the diagnostics are a little bit more electronic these days, which is not exclusive to battery electric equipment, but definitely something we've also taken advantage of. So I would say that the rate of oil consumption in the machine, the weight of filter replacement is less because we don't run the hydraulic system as much. It's not running continuously. We in fact shut down the hydraulic system if you're not turning or dumping or doing something with one of your hydraulic functions. All of that system stops completely. So there's a longer life for your oils, but it still has grease and pivot points and bearings and bushings and a lot of the same conventional systems.
Thank you. And since the upfront capital cost of BEV, batteries and chargers is often larger than a diesel equivalent. How substantial are those TCO savings?
Yeah, that is another thing that we are working to kind of shift the understanding, right? It's a different cost model, but when you look at the full total cost of ownership of the machine, you end up actually with a slight benefit with battery electric equipment. And really the offsetting cost is, and we're not talking about ventilation savings or infrastructure savings, we're talking just about diesel fuel, parts consumption, oils, filters, all that kind of thing. The biggest one is diesel fuel. And in a lot of ways, reduction in your diesel fuel consumption offsets the cost of batteries and charging systems. And then if you look at the maintenance of the machine itself, we don't have an engine. So there's no midlife engine rebuild. There's no oil changes. There's no other filter changes associated with the engine. There's no transmission. So no transmission rebuilds, no torque converter, no filters, pumps, all of the things associated with those transmissions. Those are all out of the maintenance cost equation. So we save a considerable amount on maintenance of the machine itself. And then with the added offset of no diesel fuel consumption, we end up, when you consider everything for the full life of the machine, we end up on the order of 5 to 10% better for a battery machine than a diesel machine. And that's before you talk about savings in ventilation, heating, and the other benefits that come along with it, including higher productivity.
Thank you, Brian. That was very well explained. And I think I'm impressed about, this midlife transmission rebuild. That's a huge cost. I know that. So,
yeah,
great. And also, in summary, despite the myriad of benefits, there's really not as much change required as many minds expect when it comes to this, is there?
No, and that's, I think, a key message for us, right? That we want people to be ready to move and don't be afraid of taking advantage of this technology now. It's really not that different. And we also get a lot of questions about maintenance and training of their team and everything. And the reality is, all machines are getting more advanced. They're all going to be computer-based diagnostics, computer-controlled instrumentation and sensors, a lot of wiring. And the workforce needs to learn how to diagnose and troubleshoot things with computers. And it's a bit of a shift. But it's not a shift that anyone's going to be able to avoid and still stay competitive in mining.
And that's a really good summary, I'd say, we're all going to take that shift. So if your question didn't get answered during the session, make sure to watch our Q&A. We will record one of those where I'll ask Brian all the questions that we didn't get to, but we have time for a few more, don't we, Brian?
Sure.
All right. I have one from the initial here. It's from Eduardo, who works at Vale, I think, or his name is Vale, and he wants to know, what are the substitution threats to graphite as a unique core material for anode?
That's a good deep battery question there. Graphite, thankfully, graphite's not one of those materials that's really in short supply. And actually, one of the advantages of iron phosphate is that there is no nickel, no cobalt. Cobalt's a rare commodity these days, and comes from areas where things are not politically as stable as people would like. But on the carbon side, one of the competing technologies for carbon is lithium titanate oxide, and that titanate oxide actually replaces the anode material, the carbon anode. And it definitely has some advantages, but one of its disadvantages is that it produces a lower voltage, which takes a significant hit on energy density, but does bring with it a lot of benefits in terms of volatility as well as power capability. Increased power, increased cycle life, but significantly decreased energy. And it is a little more costly. So it is a technology that we're tracking, and We see it as viable for hybrid applications and applications where we need really, really high charge rates and high discharge rates without as much energy. But it's not something we're using in our load and haul equipment.
Thank you. And we have another one from Petro Magales Silva from the Mining Studies Center. He says that we have very limited space for handling and the battery is located in a very exposed region of the truck. What can you tell us about the battery's resistance?
So that battery, you're not looking at the battery, you're looking at a really, really heavily reinforced steel cage when you see the image of the truck. It's quite robust. We're operating right now in a mine in Northern Ontario with very, very small headings. We've got maybe less than a half-meter clearance on each side. And so those batteries take quite a beating. And the system is designed for that. You know, there's lots of steel protecting it. There's really not much concern from our standpoint. Of course, no different than for any other machine. Let's put it that way.
Thank you, Brian. And thank you so much for joining us today. We're running out of time, but we'll make sure to do that Q&A session, right? You promised.
Yeah, no problem.
Thanks for joining.
All right, thanks.
And don't miss Sandvik's Innovation in Mining virtual event next Tuesday and Wednesday. Join us for the live launch of our latest member of Zero Emission Underground Loader family, the first release of the joint efforts of Sandvik and Artisan. And of course, we'll also be back with our next live session on October 6th. We will explore the sustainability benefits of carbide recycling, so stay tuned.